Section 4.1 is allegedly about adding and subtracting polynomials. It's really only about half adding and subtracting polynomials. There's kind of a run-up to that where we talk about what monomials are, and then from there stretch out to polynomials, and then we get to the adding and subtracting. So first, monomials. A monomial, if you think mono meaning one, that just has a single term. And that's why it's called a monomial, because it just has the one term. So all it is, it's the product of a constant and a variable raised to a power that's a non-negative integer. That part is important. So the raised to a power that is a non-negative integer. So I guess obviously from that phrasing, it would mean you won't have any negative powers. You won't have like an x to the negative 2. But the other thing that you won't have would be fractions, because those aren't integers. So that means you're never going to have any roots, because a square root is the same thing as raising to the power of 1/2. So you can't have things like that. Not as part of a monomial and not as part of a polynomial when we get there. So you can have a monomial in one variable where it would look like this. So the a times x to the n, where the a is some number, right? That's going to be a constant. So that would be called the coefficient of the monomial. That's traditionally the word that's used for that. X being the variable, and then n, the power, being a non-negative integer, which then that's called the degree. So the degree is the same thing as the power of the variable that's there, at least for a monomial in one variable. For a monomial in two variables, where it looks like this, where you have a times x to the m times y to the n, then the degree is what you get when you add those powers together. So like if you had, just to make something up here, let's say if you had 3x to the 4th, y to the 5th, the degree of that is 9, because you would add the 4 and the 5 together. You'd add those exponents. So when you have the multiple variables rather than just one, that's the only thing that would really be kind of different, is the way that you get the degree, that you have to add the powers together. But we'll see it. We'll have some examples where that'll show up. So with these expressions, we want to determine if each one's a monomial or not, and if it is, then identify the coefficient and the degree. So I'm just going to get all these visible at once. There are 9 of them. And I guess the first thing is just to kind of go through and see which ones aren't monomials. So what we're looking for basically is we're just looking at the exponents. We want to make sure that the exponents are non-negative integers. So negative integers are a problem, and then fractions are a problem. But only in the exponent. So like here, that 9/8 out front, that's fine. Your coefficient can be whatever you want. So I guess I'm going to make this red, or maybe kind of a maroon, to identify the ones that are not a monomial. So that looks okay because the exponent's 2. That one's a 5. That's a negative 3. That's bad, right? And that's a negative integer. So this one is not a monomial. Next one, exponent's a 4. That's good. Here it's a 1, right? Because when it's z to the first, you don't write in the 1. It's just understood to be to the first power. So that's okay. This one's a 3/2. That's not okay, right? That's a fraction that does not reduce down to an integer. It doesn't reduce to a positive integer, I guess. So this one is not a monomial. Let's see. Next, the negative 16. That's actually okay, because it would be like negative 16 times x to the 0, right? Since anything to the 0 power other than 0 is going to be 1. So that would actually be all right. And then these, right, those are integer exponents, positive integer exponents, so we're going to be fine, right? They're multiple variables, but that's all right. So now for the other ones, I guess I'll switch back to the usual blue. So then here, the coefficient, and if you just want to think of that as being the number out front, that's pretty accurate. So here that's 3 with the 3x squared, and then the degree is going to be 2 because we have x squared, right? So the degree is just your exponent. Here, the coefficient is not written in, and when it's not written in like that, that's when it's 1, right? 1y to the 5th, you would just write as y to the 5th, right? Because multiplying by 1 doesn't do anything. So usually you don't write it in. But the coefficient there is 1. And then the degree is going to be 5, since it's y to the 5th. 3, don't have to do anything. 4, we have a coefficient that's not an integer. That's fine. Your coefficient can be something that's not an integer. So the coefficient here is 9/8. That colon didn't turn out so well. That's a little better. And then the degree is going to be 4, since we have a to the 4th. Here we already said this is kind of a weird looking one, and we said the degree of that was 1. The other thing is that the coefficient is -1. Right? Since it's negative, if it's -1, usually instead of writing -1 times z, you just write it as -z. But really this thing here, you could write it as -1 times z to the first power. Right? That's kind of extra stuff in there, but then that makes it look more like the other ones. Right? So you could rewrite it that way. But when there's no power written in, it is understood to be 1. So then the degree here should be just be 1. Then, let's see, number 7, that's kind of a tricky one because that is a monomial. It's just that the degree is 0. So the coefficient is going to be -16. But that -16, you could write it like this, as -16 times x to the 0, or y to the 0, or a to the 0, or z to the 0, right? So the degree is 0. Right? Because the variable, whatever it is raised to the 0 power. That's why it doesn't show up. Because when you raise a variable to a 0 power, that's just going to be 1. And so you wouldn't write it as -16 times 1. You would just write it as -16. So coefficient of -16, and then degree of 1. Let's see. Here, the coefficient is 3. So that's not going to be anything that's all that crazy. But then the degree... This is the one where we got to add stuff, right? Because we have the 2 variables, so x to the 4th, y to the 3rd. So you should add those exponents together, and 4 plus 3 is 7. And then we do the same thing with number 9. So with number 9, the coefficient is -5, and then the degree should be 4, because you have an x squared, or an a squared and a b squared. So that's going to be 2 plus 2, which is 4. Okay, so I think that takes care of everything that could happen with a monomial, and now we can move up to polynomials. So if you just think about that, the prefix on that word, the poly, you can think, okay, well, if a monomial, right, mono is 1, poly is many, so more than 1. So that's what we're going to have. We're going to have more than 1 term generally, although technically monomials are polynomials. Just polynomials with a single term. But usually when people think of polynomials, they think of ones with multiple terms. But technically, and you can see it with number 14, a single term monomial like 7 or like 2x to the 4th, those are polynomials. So a polynomial, it is just a sum or difference of monomials. So technically, if you have a single monomial, you're fine. Right? Because you could say, well, it's that one plus 0. Now it's a sum of monomials. Right? So, yeah, monomials are polynomials. But other than that, the new things, the idea of writing in standard form doesn't make any sense for a monomial because you only have 1 term. But a polynomial being written in standard form is if you have your terms set up so the degree goes down if you go from left to right. So, you know, like degree 4, then 3, then 2, then 1, or something like that. So the term with the largest degree is first, second largest is next, third largest is next, and smallest is at the end. And then the degree of a polynomial, because like how we had the degree of a monomial, where it was just basically the exponent, or maybe you have to add the exponents together if it's a situation where we have multiple variables. But here, the degree of a polynomial is just the degree of the largest monomial. That's part of that polynomial. So you look at the individual terms, and whichever one has the biggest degree, that's the degree of your polynomial. So like for this thing here, the degree is 4, because if you go term by term, the degree of the first term is 4, because you got next to the 4th in it. The degree of the second term is 3, because you have to add the exponents, 2 plus 1. The degree of the third term is 2, and the degree of the fourth term is 0, since that's a constant. So out of 4, 3, 2, and 0, the biggest is 4, that's the degree of the polynomial. And that's how this works. So then, let's see here. First one, that is a polynomial, because the only thing that would cause trouble, just like when we were checking for monomials, would be negative exponents and fractional exponents. Those are the things that are going to cause trouble. Or maybe something like 15. I might as well just go ahead and point this out. That's not a polynomial because it's a quotient of two polynomials, but it does not simplify to a single polynomial. So I guess once again, we could point out the ones that don't work first. And then for the ones that do, we can just do what we need to do. So I guess that kind of jumps out, that negative exponent. So that's true. This one is not a polynomial. So I'll just write not a poly. This one's okay, right? So this one, that's a polynomial. So maybe green. So poly. This one's a polynomial, right? We've got degree 0, degree 1, so that's fine. Let's see. This one's fine, right? Because we had a constant before where that is a monomial, and any monomial is a polynomial. These are trouble. So 15, because you can't reduce that to something that's a polynomial. You could do the division, but you're going to get z squared plus 1 over z. So this one is not a polynomial because what happens with this, so this is a quotient of polynomials that does not reduce to a single polynomial, right? So that's what's wrong with it. And that, I think, is kind of a brand new thing, right? Because other than that, it's been just watch out for negative exponents and watch out for fractional exponents. So I shouldn't have changed colors, right? Because this next one is also not going to be a polynomial because of that 2/3. So that one is not a polynomial. All right. The other ones are actually all fine. So like you look at this one, you go, yeah, there are two variables, but all the exponents are positive integers, so we're good. So this one's a polynomial. So is this one, because we're kind of in the same boat, multiple variables, but you look at the exponents like 4, 2, 3, 4, 0. So looks like we're good. This is kind of a weird one. That is a polynomial, because you go, well, if 7's a polynomial, 0 should also be a polynomial. Yeah, that's true. So it is a polynomial. The degree is weird, but I guess we'll get there in a minute. All right, otherwise, let's go back to the usual color scheme and then go up here where we just want to figure out the degree. So going by the individual terms, we've got degree 2, degree 1, degree 0. So out of 2, 1, and 0, the biggest is 2. So the degree is 2. Down here we got degree 0 for the constant for the 3. And then for the x, that's x to the first power, so that term's degree 1. So the degree of that thing is 1. Notice this one is not written in standard form, right? Because the x has a bigger degree than the 3. If you wanted to put that in standard form, you'd have to do this, right, as x plus 3. Let's see, 7, a constant is going to have degree 0, right? So degree equals 0. We can skip 15, 16. 17, let's see, if we go term by term, first term is a 6, because you got 4 plus 2. Second term is 4, because you got 1 plus 3. And third term is 2, because it's 1 plus 1. So 6 and 4 and 2, the biggest is 6. So here, the degree is 6. Here, watch out, this isn't in standard form because you got a 4, then a 5, then a 4, then a 0. Biggest is 5. These are the ones where you got to be careful, the ones with multiple variables, because it's easy for it not to be in standard form where you don't notice that right away. Because maybe like you're just looking at the x's or just looking at the a's first. Because I think that's sort of an kind of a reflexive response just to look at one variable, then look at the other variable. kind of in the order they show up in the alphabet. But it's very possible for these to where the biggest degree or the term with the biggest degree doesn't happen first. And that's what's going on here, because the biggest degree is that 5 in the second term. So the degree here is 5. The weird one is the last one. This has no degree. And you think, well, wait, that's a constant. Why doesn't it have degree 0? The reason it doesn't have degree 0 is because 0 would be equal to 0x, right? If you had 0x, you would typically just write that as 0. But you'd also do that for 0x squared, or for 0x cubed, and so forth. So when you have a 0, it's like, well, 0 what, right? Is it just 0 and there weren't any other variable terms? Or is it 0x, it's just written as a 0? Is it 0x to the 18th just written as a 0? Or there's no way to figure that out. So a 0 by itself has no degree. That's the one kind of weird exception. Everything else that's a polynomial's got a degree except for 0. Well, then again, when you're raising things to the 0 power, 0 is also the thing that causes trouble, right? 0 to the 0 is undefined. Everything else to the 0 is 1. So sometimes 0 can create some exceptions. All right, finally, to the adding and subtracting polynomials, which is what this section is allegedly about. Adding polynomials is easier because all you have to do is combine like terms. Subtracting, you got to be careful because you got to distribute that negative that you have from the subtraction all the way through the second polynomial. So what I would do if you had to subtract polynomials is distribute that negative and then combine like terms rather than trying to do everything all at once. It's better to do it as step 1, step 2, I think, because then that way there's less stuff that you have to like have stored in your, temporary memory, I guess, like a computer. So yeah, that's what I would do. But the addition is really straightforward because really you don't even need the parentheses if you're going to do the addition. The parentheses are just saying there's the first polynomial, and there's the second one. But you could just do it and say, all right, well then this is just going to be without the parentheses, 9a cubed plus a minus 3 plus 10a cubed minus 4a squared minus 7a plus 6. Maybe if you want a little bit of organization, you could put the terms next to each other that you're going to combine. So like we've got a 9a cubed and then plus a 10a cubed that shows up later. And then for squares, we just have that minus 4a squared. Then for just a's, we have a plus a and then a minus 7a. And then for constants, minus 3 and then plus 6. So you can do it like that. And then you can just combine these together, right? So 9a cubed plus 10a cubed, you'd say, well, 9 plus 10 is 19. So that's 19a cubed. And then there's nothing to combine with this minus 4a squared. It's the only a squared term. So just minus 4a squared next. And then a minus 7a. So that a really has a coefficient of 1, right? But you would write 1a as just a conventionally. So then you say, all right, well, if it's got a coefficient of 1, 1 minus 7 is negative 6. So I guess this one, if you want to write it like as a separate step, like 1 minus 7 times a, and then minus 3 plus 6, that's just a plus 3. And then I guess I just have to simplify this and write it as minus 6a. So, okay, 19a to the third minus 4a squared. Either plus a negative 6a or just minus 6a. And since I'm out of room, I'm just going to go to the minus 6a here. And then plus 3. And that's it, right? That right there is the answer. So the addition is not that bad. You just kind of end up combining like terms together, and that's about it. For subtraction, I would say distribute that negative before you do anything else. So if you're going to subtract this first polynomial, you can just write it without the parentheses. So minus 2p to the fourth plus p to the third plus 5p squared plus 1. But then we got to distribute that negative. So then minus 3p to the fourth, then minus 7p to the third, then minus a negative 4p squared. So minus a negative would be plus 4p squared. And then minus a negative 2 you could write as plus 2, right? Because minus a negative will be a plus. And then combining like terms again, I guess we want to put the terms that you're going to combine next to each other. We got a couple of p to the fourth terms, so minus 2p to the fourth, and then minus 3p to the fourth. Then for the p to the thirds, we've got a p to the third minus 7p to the third. Then we got a 5p squared, and then down here 4p squared. And then there's no p term anywhere, right? You can see in the original polynomials there aren't p terms either, so there shouldn't be any. Then we just have plus 1 and then plus 2. All right, so negative 2 minus 3 is negative 5, so minus 5p to the fourth. Then 1 minus 7 is negative 6. We just had that in the last problem, so minus 6p to the third. And then 5 and 4 is 9, so plus 9p squared, and then plus 3. And that's it. All right, not too bad so far. The next one where you have multiple variables, I guess the main thing to remember is that if you're going to combine terms, they have to have the exact same combination of variables. So you can have degrees that are the same where you can't combine those terms. Like for instance, we're not going to combine the 3x squared y with the 5xy squared, right? We're only going to combine x squared y terms with other x squared y terms, and we're only going to compare xy squared terms with other xy squared terms. So you don't combine everything with the same degree. It's going to be everything with the same degree and x raised to the same power and y raised to the same power. You can combine that. All right, so since we're subtracting, again, we're going to distribute the negative before we do anything else. So first one you can just write as it is without the parentheses, so 3x squared y plus 5xy squared minus x, and then distributing the negative, minus 7x squared y, and then minus negative 5xy squared would be plus 5xy squared, and then minus 3y. And then let's see what we can do. There are two x squared y terms, two xy squared terms. I guess I can put them next to each other. So 3x squared y minus 7x squared y, and then plus 5xy squared, and then another 5xy squared. And then other than that, we just have the minus x and the minus 3y. So I guess I'll just put them in that order. And I actually have everything written in standard form right now because the degrees are going down to the extent that we can do it, right? I mean, we're going to combine terms here. 3 minus 7 is negative 4, so we get negative 4x squared y. And then 5 plus 5 is 10, so plus 10xy squared. And then minus x minus 3y. Not a whole lot we can do with those. All right, so yeah, degree 3, degree 3, degree 1, degree 1. That's about the best I can do to get it into standard form. The other thing that might be worth doing, and I haven't done it yet, but I'm going to do it on the last one, is that when you start rearranging things and then combining terms, especially when you're combining terms, to kind of cross out the ones that you've already used. And actually, I was going to box in the answers, but I don't want to use the same color because everything's kind of cluttered in here. So let me box in this guy and this guy and this guy. And then we can get to the last one. All right, so this last one, it's got both adding and subtracting. So we're supposed to subtract and then add. What I would say is distribute the negative for the subtraction, and then we're just going to combine terms together willy-nilly. That's the best thing to do, I think. So this first polynomial we can just write as 3x cubed minus 2x minus 1 without the parentheses. But then we're subtracting here, so we got to distribute that negative. So minus 2x cubed, then plus 4x squared, and then minus negative 3 is plus 3. And then we're just adding this one, so we can just put that right in there without parentheses, plus 5x squared minus x. And now we're going to combine terms together. And if you look at what's here, we got cubes, we got squares, we've got x's, and we've got constants. All right, what I'm going to do, I guess, first of all, just to rearrange everything, cubes first. So we got 3x cubed, And here's where I'm gonna cancel terms out after I rewrite them, just to make sure that I get everything and that I don't duplicate. So I got that one, and then minus 2x cubed. All right, I got that one. That's all the x cubed. So then x squareds plus 4x squared. We got that one. And then plus 5x squared down toward the end. We got that one. X terms, we got a minus 2x back here. All right, so that one's off the board. And then minus x at the very end. And then other than that, we just have a minus 1 here and then a plus 3 there. So minus 1 plus 3. And I guess that would be all of it. Okay, good. Because now we can combine terms and we can say, well, 3 minus 2 is 1. So that's a 1x cubed, or just x cubed. 4 and 5 is 9, so plus 9x squared. Then minus 2 minus 1 is minus 3, so minus 3x. And then negative 1 plus 3 is 2, so plus 2. And there we are, right? There's the answer. I guess if I'm boxing them all in dark green, or forest green, or whatever you want to call this, I'll do it to this one too. There. So this one looks like it's going to be more intense because we have to do the subtraction and the addition, but it ends up not really being too bad. Just distribute the negative for the subtraction, and then you should be able to combine stuff. There's more stuff to combine though, which is why I crossed everything out when I rewrote it. And if you want to do that all the time just to be safe, there's nothing wrong with that. I used to, but now it's like there's some threshold in my brain where there are points where I think that's a small enough number of terms where I can get away without doing it. And then when it goes over it, I'm like, I better cross stuff out now. So sure, if you want to do that all the time, there's nothing wrong with it. But that's basically it for section 4.1.